Hello and welcome to this chemistry lecture series. In this video, we're going to look at chapter 17, section 2, which is going to focus on the reactions to make alcohols. So these are reactions that are either going to add an OH group, a hydroxyl group to a compound, or substitute an already present group for a hydroxyl group. Now, alcohols sit in a very weird place when it comes to the reactions to make them and our curriculum. And that's because half of the reactions to make alcohols we have already studied in chapters 15 and 16. And the other half of the reactions to make alcohols we will study either later in chapter 17 or in chapter 18. So this is essentially a review and preview kind of section. So let's begin with the review. So alcohols are actually something that we've seen multiple times because they come up in chapters 15 and 16. We learn how to make alcohols from alkenes in two different ways in chapters 15.3 and 15.4, and we learn how to make alcohols from halogenoalkanes in chapter 16.2. So let's review those reactions really quickly. We can grab alkenes and convert them to alcohols through two different reactions that we learned in chapter 15. The first is electrophilic, and let me make this a little bigger. The first is electrophilic addition. So electrophilic addition was a reaction that broke the pi bond in our alkenes and added something across the double bond. In the case of the reaction between alkenes and steam, we were able to make an alcohol. So when an alkene reacts with steam, which is heated water in the gas state, so this will not work with just regular water, it has to be steam. Those are our reactants. When that reaction happens, an alcohol is created. Now, the reaction does require a catalyst. The reaction with steam and alkenes, in order to make an alcohol, require a phosphoric acid catalyst, H3PO4 catalyst. So we're going to have our catalyst in there as well. So something like, for example, propene, propene, we see right here, reacted with steam in phosphoric acid catalyst to create propanol. And if you remember, this could create two different reactants or two different products. The first was what we see here, where the OH hydroxyl group is added to the central carbon, and that will be our major product, according to what we studied in chapter 15.3. Because the OH is added to the secondary carbon instead of the primary one. The other product will be CH3, CH2, CH2OH, where the alcohol gets added to the terminal carbon, the one at the end, which is a primary carbon. But this will be a minor product. The secondary alcohol that gets created is the major product of the reaction because the secondary carbocation that leads to this product is more stable than the primary carbocation that leads to the primary alcohol. Another one of the reactions that we saw in chapter 15 that would create an alcohol was the oxidation of alkenes. So oxidation reactions of alkenes could be done, but they will not just create an alcohol, they will create a diol. So the oxidation of alkenes would create a diol as a product instead of an alcohol. And this is just an alcohol with two OH groups instead of one. In this reaction, we will react the alkene with cold dilute potassium permanganate. So alkenes will get reacted with potassium permanganate or KMnO4. And again, this reaction could also happen with potassium dichromate. So keep that in mind. You might be presented this reaction with either potassium permanganate or potassium dichromate which is K2Cr2O7. Oops. So the other option will be K2Cr2O7, which is potassium dichromate. Both the potassium dichromate and potassium permanganate reactions would have to have a specific condition to happen. And that condition is going to be the cold and dilute states of our potassium permanganate or potassium dichromate. So when this reaction happens, it needs to be in cold and dilute conditions, so not concentrated, not hot. The conditions are going to be cold and dilute, and that will create a diol. So here, for example, we have, again, the exact same alkene that we used before, propene, reacting with the O's in brackets. And remember, this represents our oxidizing agent. So that represents our potassium permanganate or potassium dichromate and water to create our diol. In the case of a diol, we would not have a major and a minor product because we will have two hydroxyl groups. One will be added to one side of the double bond, to carbon number 1, and the other one will be added to the second carbon. So here we have carbon number 1 and carbon number 2, just to show where they are in the products, and each of those will get a hydroxide or hydroxyl. So we wouldn't have a major and a minor product. I will say also, we're not showing here because we already covered this in 15.4, but do remember that this reaction, because of potassium permanganate, would have an observation. And that observation is the potassium permanganate going from purple to colorless, or to clear, to colorless. So if we use potassium permanganate, and this is true of any reaction that uses potassium permanganate, the potassium permanganate will go from purple to colorless as an observation. In the case of the dichromate, we also get an observation, which is that the dichromate will go from orange to green. Oops, let me change my colors here. To green. So we'll get a color change with the dichromate, but the color change would be different, and the dichromate will go from orange to green. So do remember those color changes depending on which conditions, which oxidizing agent we use. And that's going to be the same as any oxidation reaction where we use one of these oxidizing agents. Now, the last reaction that we saw in a different chapter, chapter 16 this time, that would create an alcohol is a nucleophilic substitution reaction of the halogenoalkanes. In this reaction, we would be able to react a halogenoalkane with aqueous alkali in a hydrolysis reaction or nucleophilic substitution reaction. So remember, this reaction is actually both a hydrolysis and a nucleophilic substitution, because hydrolysis can be a subsection of nucleophilic substitution reactions. But if we reacted a halogenoalkane with aqueous alkali, and remember, aqueous meaning that there's water involved, and alkali meaning some form of water-soluble base. So our two common alkalis will be NaOH or KOH. Let me put a little more space there. Or KOH, both of those will be very common alkalis to use. But if we react these with a halogenoalkane, what we essentially get is a substitution reaction where the halogen gets substituted with our hydroxide ion, which will create an alcohol. So there is a specific condition that we need for this reaction, and that condition would be the fact that this needs to be under reflux, which remember is how we heat organic compounds so that they don't just evaporate on us but actually react. And this reaction could also occur not just with an alkali but with water. And with the water, it would just be a lot slower. So We can see here how 1-chloropropane could react with sodium hydroxide under reflux to create 1-propanol, CH3, CH2, CH2OH, and in this case, sodium chloride. So we learned this reaction in chapter 16.2. So these are the three reactions that create alcohols that we have already studied in our prior chapters 15 and 16. Now let's look at the preview section. Let's look at the reactions we will study in different sections that are going to come up that will create alcohols. Now with these reactions, these are usually because the reactants are things that we haven't studied yet, like aldehydes, which are part of chapter 18, or carboxylic acids, which are parts of later sections of chapter 17. So, what are these reactions? I'm going to go over them really quickly. I'm just going to point out the reactants because we will look at the specifics of these reactions in those later sections. But in the first reaction, we see that the reduction of an aldehyde can lead to the creation of an alcohol. In this type of reaction, we will react an aldehyde or even a ketone. So this will work with both types of functional groups. So we will react an aldehyde or a ketone with a common reducing agent. So just like we have common oxidizing agents like potassium permanganate and potassium dichromate, we have common reducing agents, which are LiAlH4 and NaBH4. So you'll notice that our oxidizing agents have a lot of oxygen in them, as the name implies. Our reducing agents have a lot of hydrogen in them. So NaBH4 or LiAH4. So when we do this, when we grab an aldehyde or a ketone, and we react them with common reducing agents like LiAlH4 and NaBH4, we will produce an alcohol depending on what we're reducing. Aldehydes would reduce into primary alcohols as our products, whereas ketones would reduce into secondary alcohols. So depending on which type of functional group we reduce, whether it's an aldehyde or a ketone, we'll get a different type of alcohol, but an alcohol nonetheless. So if we were to reduce something like propanol, CH3, CH2, with our reducing agents, which we're just going to simplify as hydrogen in brackets when we reduce, we will get a primary alcohol like 1-propanol. If we were to reduce a ketone like propanone with one of our reducing agents, we will get a secondary alcohol like 2-propanol, like we have here. But we're going to look at this reaction in more detail in chapter 18.3. But here we have the basics of them. Another way to create an alcohol, which we'll see later in this chapter, in chapter 17.4, is the reduction of a carboxylic acid. We can reduce carboxylic acids, which I'm going to highlight here. So we can reduce carboxylic acid again, and we're going to use our common reducing agents. So either LiAlH4 or NaBH4. We're going to reduce these carboxylic acids into an alcohol as well. So for example, if we reduce something like ethanoic acid, CH3COOH, with our reducing agent, we will get an alcohol, in this case ethanol, and water. And again, we'll look at this in sections 4 of this same chapter 17. The last reaction, which we'll also see later in this chapter, 17.3, is the hydrolysis of an ester. So esters can undergo a hydrolysis reaction where we will essentially break them apart, and one of the products that we create is an alcohol. So esters can be heated with an acid or a base to hydrolyze them. So an alkali or an acid will be our reactant with the ester. And we need some special conditions to do this. Our conditions in this case are, let me highlight them here, that where is my highlighter? We need to have the ester be heated and the acid or alkali be dilute. And again, whenever we see the word dilute here, remember that dilute means dissolved in water. So that means aqueous, or the fact that there's H2O present. That's what makes this hydrolysis reaction. Oops. There is water present in our reaction because the ester or the base are dilute, meaning they're aqueous, meaning there is water involved. So if we heat up an ester with dilute acid or alkali, the resulting or one of the resulting products will be an alcohol from that ester. Now, when we do this, we do actually get not just one, but two different products. The first product is a carboxylic acid, and the second product is an alcohol, which I don't actually believe I have one here, but I'll just highlight it here at the top. It's an alcohol. So, we're gonna look at that reaction in the next section. But for example, if we have something like CH3, COO, CH2, CH3, which is ethyl ethanoate, which is the ester here, and we reacted that with either an alkali or an acid, we will get two products, a carboxylic acid and an alcohol. That carboxylic acid, if we use a base, would be ionized into a carboxylate ion. But again, we'll look at those details in section 17.3. So this is the preview section. These are the three types of reactions that we have yet to study, that we'll study in chapter 18 and 17, that create alcohols as a result. So we have a lot of different reactions that create alcohols. 3 which we haven't seen yet, and 3 which we have already studied. So just keep that in mind as we go through this chapter and as we look at the reaction webs at the end of the chapter. That's it for section 17.2. I will see you all in the video for 17.3, where we will look at these hydrolysis reactions of esters as well as other reactions of alcohols.